129S, and we're down to, let me get this. All right. We're down to this one, session management. I've canceled the next week's class, so don't come. I'll be at Wild West Hacking Fest. I won't be here next week, Wednesday, Thursday, Friday, or Saturday. So the Wednesday class will go on remote only, so people who want to come physically to the lab. The next day this lab will be open is Monday, and then not again for a whole week. Anyway, so let's talk about session management, which is Chapter 7. All right. There we go. All right. So, the point of session management is to remember something significant about the user, like, for example, they have logged in. And, therefore, you have to somehow mark them as being logged in, and all later requests have to somehow tell the server over and over again that they've logged in, because the server forgets everything after every request. So if you can overcome the session management, then you can elevate yourself to administrator or horizontally escalate to another user. And sometimes this might be very easy, like there might just be a number for your session management token, and just adding one to it might get you in. They got in my Gmail at DEF CON around 2011 because I thought Gmail used HTTPS, but all they did at that time was use HTTPS during the login process, so your password was encrypted, but then they switched to HTTP and sent an authentication token in the clear, which could be stolen. So they stole mine, and that put me on the wall of sheep. If you go to DEF CON, people try to steal your logins, and then they put you on the wall of sheep to embarrass you. So, happened to me. I didn't get upset about it. It's educational. Anyway, all right. So Web 1.0 was the original internet. It's just stateless pages like my page, where you can look at the pages, but you never log in. You can't post comments. It's just like a bulletin board with pages on it. Now, after that, you had things like Facebook and everything where you want to log in. So this means you have to somehow remember that you've logged in. If you don't have a login, you might still use sessions for other things like filling your shopping basket or targeting advertising or something. So basically, when you do log in or do anything else that somehow makes you a special user, the server will send you a set cookie request, which will now set the name of a cookie. This one's ASP.NET session ID, and then a value. And then your browser will remember that, and every request back to the same domain will include that until the cookie expires. So there's two categories. You can either generate session tokens in an unsafe way so they can be predicted, or you can handle them incorrectly so they can be stolen. All right, now one thing that happens is most real modern websites have a ton of cookies in it. If I go to Amazon.com and I use BERT to examine the request, you can see it has about 10 or 12 cookies. And most of these are not to authenticate you. They're for some other purpose, like maybe for ad targeting. So what I did is I log into my Amazon, I go here, play it through BERT, and over here on the right I can see it knows who I am. My name is over here somewhere. Yep, right at the end. And then I just delete cookies until it forgets who I am. Then I can find out how many of these cookies are actually used for me, and the answer is 1. Just the Xmain cookie is the only one that needs to know who I am. All those other cookies are doing something else. So that's a way you can find out what's going on a website. All right, there are alternatives to sessions. There are other systems built into Windows that will automatically log in, but these are used typically only on local networks and not on the internet, the basic digest and TLM authentication. Then there are sessionless state mechanisms. This is another way to do it. Rather than issuing a session token or managing the state, it will send all the data required for the state to you as a big blob of data, which will come back as a cookie. This is fairly popular, and ASP.NET's view state is designed for this. We've talked about it before. So you can put a bunch of data here and create an array, and then you can make a view state of this in your code. And you can put any kind of data you want in there, hash tables, strings, integers, Boolean values, and then it can be protected. And it better be protected. So it's usually a binary blob that's encrypted or signed. ASP.NET view state is base64 encoded and adds a hash, including your machine authentication code, including the machine's MAC address. And it has an expiration time. So the result is you have this big blob of data in one of the cookies in your browser. So you can recognize these things by big blobs of data, and the data is encrypted or signed, and an application will reject attempts to submit the same item with more than one request. This is why every time I use BERT Reader, the first thing I do is run the request without changing it, because a lot of modern techniques will not let you repeat any request. And this is why the instructions in the Web Security Academy training always say turn on the interceptor and modify that, because that's what generally will work. Using a repeater will only work on relatively older sites, but it's easier. All right. So token generation. So this guy figured out how to break into token generation. He found that the password reset used a 6-digit code, and they're rate limited, but on beta.facebook.com they were not rate limited, so he used Burp Intruder to break a 6-digit code and got $15,000 for that bug bounty. So the password recovery tokens are sent to a user. You also use tokens in hidden form fields to prevent cross-site forgery attacks, where you move from one page to another in an unexpected order. You can use them for one-time access to remember you and to remember customers to see the status of an order, lots of things, but all these depend on the token being unpredictable. You make this long random number, send it to the user, and you hope that nobody else can guess or find out that number. Now, some people use meaningful data in the tokens. This is not considered a best practice, but it is done. So they have a token like this that looks like random letters, but it's not. It's just a hexadecimal ASCII for this, user equals daf, admin, date, usual stuff. And so therefore, once you know that, you can modify this token to say like user equals admin, and it might work. And the ASCII, hopefully you know your ASCII tables, but if not, I put one here so you can consult it. It turns every letter in English into a number. So you can put in there like the username, an American identifier, email address, date, time, that sort of thing. And then you can encode it with XOR, with something, or base 64, or hex codes. All these are ways to manipulate meaningful data so it's not as obvious what it is, but it's pretty easy to decode. And so you can try this here. To contain a single token by logging in or something, then try modifying it. Change it 1 bit at a time or 1 byte at a time. See if it's still accepted. And Burp has a thing called char frobber to do this in an automated way. Log in as several users at different times and record the tokens and see if you can spot the pattern. I've done this a few times. One trick I used was to make shorter and longer passwords on a site where and then my encrypted password was shorter and longer, so that proved that they were using some incredibly simple system like XOR or Caesar cipher. I've also used one recommended by your book, which is 32 identical characters, because that'll be encoded, if you're using AES, as 2 blocks of 16 characters, which will repeat if they're using electronic codebook version of AES. So you can find weaknesses by analyzing how they generate this thing. Look for correlations. A series of repeating characters will sometimes show the repeating output. Base 64 often ends in an equal sign. All right, so that's the plan. Check and see if you can modify a token and get something to load. Let's try a Kahoot. This is 7, I think. Yeah, 7A. All right. All right. So what encoding looks like that. That's MD5. I was puzzled by it. It's not base 64 because there's no capital letters. And it's not XOR, or this AAs would be repeated. This is an MD5 hash, a long hexadecimal number. All right, anyway. All right, how about that one? That's hex. You can see the capital A is 41, and you have repeated 41s there. All right. How about this one? That's base 64. Capital letters, lowercase letters, and numbers. And often an equals at the end, but not always. There's only an equals at the end if it needs padding. It can encode 3 characters into 4 bytes of base 64, and this is a 9-character string, so it doesn't need any padding. All right, how about this one? That's XOR. Sheet to 41 has turned into 05, and it repeats over and over. So this is single byte XOR, where it changes every byte into a different corresponding byte. All right. Come on. Escape should have there. It does. All right. So, your tokens might be predictable. Oh, let me see if I can get the chat to appear. Well, I guess I got it over there. All right, doesn't matter. All right, so, all right. So you might be able to guess valid tokens just by looking at the pattern. All right, and you're getting a large bunch of tokens and doing statistical analysis is an option. Here's one where it's just a sequential token. There's some kind of payload here, just trying different numbers until you get some numbers that are accepted. And so it shows at the top the ones that actually authenticated as somebody. So by logging in as one person, you were able to turn yourselves into all these other people by just changing the token number. So you might have concealed sequences, time dependency, or random numbers. Here's a sequence that appears to be base 64 encoded, but if you decode it, you just get garbage. What these are is long integers. If you just turn them into integers and then look at them, they still look random. But if you subtract them and get the difference between them, you begin to see a pattern. And if you realize that one of these is just a negative number, then you get the same difference between each one. And so what this is just a straight line. It just adds this number every time and keeps only the lower bits. So it looks random, but it's not random at all. This is called linear congruential random number generator, and they're all over the place. A lot of the default random number generators in programming languages work like this or some other stupid way, so they're not good enough for real cryptographic work. All right, so you write your own Python script to repeat it and predict those numbers. All right, and all right, here's another example. You have 2 numbers. The first number just goes up by 1 for every user. The next one goes up by a different amount. So if you look at how much it goes up by a few hundred each time. So then if you wait till 10 minutes later, the first number is jumped, but the second number is jumped by this, which is approximately 10 minutes in milliseconds. So the second number just seems to be the time in milliseconds, and the first number is just counting up the users. So that means all you have to do is poll the server to gather tokens, and when you see a gap, if this number goes up by 2, you know there's a user in the middle, and you know their token is in this range, which is not very big, from like 400 to 1100. So it would be pretty easy to find that token. And there's a lot of weak random number generators. Here's a linear congruential number generator, multiplies a number by a constant, adds another constant, and keeps only lower order bits. So if you know this is it, after you find one value, you can predict all the others. And this kind of thing tends to happen. PHP did this stuff, combined a few things like the client's IP address, the time, token creation, and the microseconds, none of which are that hard to predict. So this guy, a hacker, wrote a tool to hone things based on PHP's random number generator. All right. And so what you can do is assume they're randomly generated, try a bunch of tests, and see if it passes the test to be random, and then you'll find out what part of it is not random. And Burp has a tool to do this. It'll show you how many bits are random and how many bits are not random in a multi-bit token, so you can do this sort of thing. All right. And then you can have encrypted tokens, where you're going to take meaningful data and encrypt it with a secret key not known to the attacker. You might think this is safe, but it's not unless you do it wisely. If you use electronic codebook ciphers, they don't actually hide data very well. The problem is, this is a classic textbook encryption. You take a block of data, encrypt it with a key, then you take another block, encrypt it with the same key, and keep going. Well, what happens if you have a pattern like this, where you have a block of white, and then another block of white, and another block of white? They're all exactly the same. Well, they all encode to the same block. So you don't really remove all the information in the image. Repeated blocks make repeated blocks of output. So this is a flaw, and this means you can exploit it. So for example, if you encrypt this, a random number, a user ID here, a username there, and a few other things, then the encrypted form appears meaningless, but this was encrypted with something that only encrypts 8-byte blocks. So each of these 8-byte blocks is separately encrypted, and you can just rearrange them, even though you can't decrypt them. So for example, if I take this line here and repeat it here, then user ID is now 992. Instead of where original user ID was 218 for this user, but by just repeating one of the earlier blocks here, I can make UID equals 992. And this also exploits another fact about web servers. You can define something and maybe define it twice or 3 times by sort of mangling this, and it'll be okay. Like here, I got app equals 218, and here I app equals iTradeEU. Most web servers will not crash or anything when you do that. So, all right, and what you can even do more, you can assign a new user with a name carefully crafted, DAF1, to have the 1 roll around here, and now you have a line with a 1 there. You can put that line up here and become the administrator, which is typically UID equals 1. So even though you can't decrypt the data, you can just reshuffle the blocks and create new strings that will be interpreted by the server, even though you don't have the key. So CBC is another technique to try to overcome this, where you have an initialization vector in addition to a key, and you take the output of each block as the initialization vector for the next block. So this solves the original problem. If you encrypt an image, the image now looks random without any patterns in it, but it has another flaw. Suppose you encrypt this meaningful data. The thing about cipher block chaining is if you change a single block of the ciphertext, it scrambles this plain text into garbage, but it changes only 1 byte of this, because this output of this encryption is just XORed with this. So you can now make single byte changes in the plain text as long as you're willing to scramble part of it. And like I mentioned, web servers will typically tolerate this. If some of this is just turned into garbage, they'll just go ahead with the rest of it. And frequently it doesn't matter that you don't have this number anymore. So now you can change these numbers one by one, 1 byte at a time, even though you don't have the key. You can, changing 1 byte here will change 1 byte there to a random value, but you can just go through all possible values here. So that's a trick, and so you can just try it. And there's a tool in Brit will do. You just keep changing one thing, and this is what the decrypted things looks like. And eventually, UID changes to 226. You manage to change this number, so now you'll log in as a different user. If you just try changing 1 byte at a time, modifying this session cookie, And you flip each bit, which is an option in burp. And here's the results. Most of them are invalid, but a couple of them actually reach other people, which can happen if you're using that kind of encryption. All right. Another thing that might happen, which has happened, I think, to Facebook and others, they may reuse the encryption code elsewhere. So you can find a way to use their code to decrypt things or to re-encrypt them. This was another big body at Facebook. Somebody found that the random thing they sent you to reset your password was actually the same random number that was used somewhere else on the page you could see. So they were able to find it. All right, let's try 7B. All right, which token type often uses the same value every time the user logs in? If you're encrypting meaningful data, it will probably be the same every time unless they remembered to include something that changes, like the time in it. All right. Which one can you exploit by rearranging blocks of ciphertext? That's electronic codebook. Each block is encrypted independently. All right, which one can you exploit by changing a single byte? That's cipher block chaining. All right. Oh, it's not done yet. Okay. Which one uses one block of data to influence the encryption of the next block? All right. That's cipher block chaining. That's how it works. So, Your token handling, people have thought HTTPS solves everything. The only thing it stops is eavesdropping from people near you on a wireless network or somewhere in the path between you and the other end. The problem is the cookie can be stolen. Anyway, now you might transmit it without encryption, then it can be sniffed from anywhere where the data passes through. And that can be pretty serious. For example, these days people might have two-factor authentication, so stealing a password won't get you in, but stealing a session cookie will get you in. And you won't need to do the two-factor. Now, this used to happen, like I mentioned, some apps used to use HTTPS during login, but after that use HTTP and send a session cookie that could be stolen. Almost nobody's doing this anymore. Everybody's pretty much 100% HTTPS. But you could use an HTTP site and then update HTTPS, and that might continue to use a token that has been transmitted in an unencrypted way, and maybe you could use a back button to trick the browser into emitting it, although I think that's not likely anymore. SSL Strip was a very famous product to help promote moving to HTTPS, where you just set up a proxy, and you can do this with the burp proxy, so people connect to you over HTTP, and then you connect to the server HTTPS. It's pretty nasty. The user won't see an obvious problem in the page. Anyway, all right. And there used to be mixed content pages where HTTPS and HTTP content mixed on the same page, which is a very unsafe practice, and I'm glad to see I don't see it that commonly anymore. So you could send someone an HTTP link, and then if they go there, it might send that session token over HTTP if they didn't to set the cookie to be secure. All right. So you can wander through these things, watch how it moves from HTTP to HTTPS. And I think I'm not going to bother with these demos because we'll see better stuff in the Web Security Academy. The point is, this one just had the username in the cookie. Username equals user. Now, if you set a secure flag on a cookie, the browser will only send it over HTTPS, so this should be pretty much set on all cookies these days. And if you do that, then you won't be able to get in. HTTP only and secure. All right. You won't be able to steal the cookie. You just put the secure flag here, and this is the PHP page to show you how to set a secure cookie. So here it is, setting a cookie. Username is user, and it sets secure HTTP only. So those both help protect it. The secure means it can only go over HTTPS connections, and the HTTP only means it cannot be loaded by JavaScript, just by HTTP. So it's very difficult for someone to steal, even with a cross-site scripting attack. Although you have to realize both of those are asking the browser to please obey that rule, and you have no proof that the browser actually did obey that rule. All right, so if you send a secure cookie to an HTTP page, the cookie will not be sent. That's the point. All right, and then you won't know who you are. All right, if you go to secure cage, then it'll go in. So anyway, that's all I wanted to show you. All right, now this thing, HTTP Strict Transport Security, was an enhancement where once you receive a header that you should only talk to this site over HTTPS, the browser will forever after just use HTTPS. A few years ago, quarter websites were doing this. I'm not sure where it is now. These days, I think it would be okay for your browser to just assume every site is HTTPS. There's really very few HTTP sites left. Anyway, all right. If your token is disclosed in a log, that's not as common, but the log is more visible to the world. So if you just Google, I wonder if this still works. This is a Google dork that used to work, and maybe people are still falling for this. JSession ID. Yeah, here's people warning about this problem. I wonder if there are any JSession ID pages that are just logs created by this. They would have an automatically generated page title, not this. These are all pages about the vulnerability, not pages that demonstrate the vulnerability. That one might be. Take a look at those pages. They might be open logs. Nope. All right, anyway, I'm not sure I'd find a good one, but you might find one where it just has a session ID right up here in the URL. And that's the point. If you put a session ID there, then it will be in logs, it'll be in servers, and so on. It'll be in favorites. That's why you shouldn't put secrets in there, but people do. All right, so some of those pages might actually have had that vulnerability. In fact, let's take a look. This one here does. It's not loading, but it has the JSession ID right up there. And that's a really bad place to put it. All right. Another issue is the referrer logs. If I get you to go to my page, your browser will send me the whole URL of where you came from in the referrer field, and I'll get your session cookie. All right. So that's the referrer attack I was just talking about. All right. So if you get the same token every time you log in, that's the kind of thing you might have. And this means, this is, as far as I can tell, related to a vulnerability I'll show you in a few minutes, where this old cookies still work. So here's the logic where you have the username and then some kind of authentication, but I can just change the username and the same authentication will let me in another person's account. That's the kind of thing you might find. This is something I found almost universally on the web, or at least half the websites I tried a few years ago had this flaw, where logout doesn't do anything. All logout does is delete the cookie from your browser. It does not invalidate it on the server. So I checked. After I found that Office 365 had this problem, I found tons of websites with this problem, where you can log in, get a cookie, steal the cookie, then log out, and you can still get back in using the old cookie. It was never invalidated. This is really bad. This means if somebody steals your cookie, they're in. Even if you change your password, the old cookie still works. The only thing you can do is delete your account. It's a really serious flaw, and I know at least one site changed their policies when I told them, but I wouldn't be surprised if a ton of them are still doing it. All right. Another trick is session fixation. If it's going to be in the URL, I could send you a URL to click that has the session cookie already in it. And maybe it will just continue at that same session after you log in. I can trick you into submitting a request that goes to an attacker's server, so I get your cookie. The cookie might be too liberal in scope. By default, subdomains are included. So if I set a cookie at games.samsclass.info, it will be sent to foo.games.samsclass.info. That's a subdomain of games, but not to samsclass.info. So that's an issue. So, all right. So example, you have blogs.com, and people are logging into blogs.com for each user, and then they create their own blog, joe.blog and sally.blog. The problem is their blogs.com cookie will be set to all of these. So a blog at sally.com could get Joe's cookie. The better solution is to have www.blogs.com for the main site, and then it won't go to joe.blogs.com. That won't be a subdomain of this site. So that's an issue. First time I ever heard any reason to use this www either. People are always putting that in front of every website, and for years I never saw any reason to do that. You see, I never did. All right, so you return a HTTP header, and you can specify what path this cookie applies to. So that's a thought. All right. Anyway, session management, you generate strong tokens, protect them. You should have good random number generators, so they're really random and not predictable. They shouldn't be encrypted data. And you should get good source of randomness. By the way, this is cute. You add a secret, then hash it all. Change the secret on reboot. This just happened to a brand of firewalls this week. They had a vulnerability, and they got hacked months ago. People patched the firewalls, and they thought they were fine. And it turns out that months ago, they stole the seed for the random number generator, and they can now predict the two-factor tokens. So they're still getting in to the two-factor authentication of those firewalls, even though they've been patched. Anyway, so transfer them only over HTTPS. And you should really log out. When someone logs out, the session tokens should stop being valid on the server. I was horrified to find out how many sites do not do that. Sessions should expire. Yeah. The only people I know that do that are major credit card companies. And you should remove cross-site scripting vulnerabilities. That would be nice. Don't accept tokens submitted by unrecognized users. Use two-factor authentication is a big thing. Use hidden fields rather than session cookies. Those tell you that someone actually came from the page you intended for them to come from. It prevents people from using pages out of order. All right. And you can make a per page token created each time. This is what you do. Each page has a hidden token that's random, and when you go to the next page, it checks to make sure that hidden token was submitted, and that means you really came from my page. You're not just in Burp Repeater or some other tool that lets you submit requests out of order. All right. So you have something like here, like a value that's random each time, and there'll be a per page token here. Screen token has a value. All right. So request with invalid tokens should raise IDS alerts, and you should terminate a session if you're being hacked. You've found suspicious inputs. Let's try another Kahoot. All right, so what does HTTPS prevent? Yep. If you sniff the wireless transmissions, they'll be encrypted and you won't be able to read the data. All the rest of these attacks can work. All right, what defense prevents users from clicking through an SSL warning? One of the features of HSTS I didn't mention. That's one thing about telling the browser this page should be loaded securely. From then on, it won't accept a bogus certificate for it, apparently. I haven't heard anything about that in years. I wonder if its deployment is actually rolled out and if it's actually helping. Anyway. All right, what defense protects cookies from theft by JavaScript? That's HTTP only, of course. Good. All right, what should a logout button do? Yeah, they should terminate it on a server. Most of the time, they just delete the cookie from your browser, which is not the same thing. What kind of session token is not sent on every request? Hidden fields only are sent on that one page, so this is a per page token, so you can verify what page somebody came from. All right, what should happen if you receive a request with a modified hidden form field? Yeah, terminate the session, perhaps raise an alert. You know, this is an attacker attacking you. You shouldn't just let them continue to perform business as usual.